Inglês é melhor, né?
É?
Inglês, né?
So the next speaker is Frederico Girão from Federal University of Ceará. He will speak on an example of Fenchel-Type inequality in hyperbolic space with application to a Penrose inequality.
Okay, thank you so much. I want to thank the organizers and especially the Tang for the invitation. It's a great pleasure for me to be here. Okay, so this is joint work with Levi Lima, also from UFC. How do I pass the slide? Just here? Oh, yeah. Thank you. All right, so let us recall what the Alexandrov-Fenchel inequality in Rn is. Okay. So this sigma k is the elementary symmetric function, the kth elementary symmetric function. And then the inequality says that the integral of sigma k, okay, the kth curvature greater than or equal than a power of the kth minus 1 curvature. Okay. All right, and you have this constant here that you get this constant when you plug in the sphere. Okay, so the sphere gives you the best constant. And there is also a rigidity statement, okay, saying that the round sphere is the only one that gives you the best constant. Okay. Okay, so the first proof that appeared of this inequality used this theory of mixed volumes. So they need a convexity. But recently, and the paper was showed up in 2009, but like if you go to the archive, it's actually from 2007. Guan and Li, what they did was they used some curvature flow, some inverse curvature flow. And they used a result of Hugheskin, saying that they had to prove a similar result, saying that on Rn, if you have a star-shaped and k convex, which means the sigma I are all greater than or equal to 0, then this flow exists for all time, okay, and converges to a sphere. Okay, so they were able to prove the inequalities using this flow. Okay. Okay. So what is the k equals 1 case? Let's see. When k equals 1, you have the integral of the mean curvature on the left-hand side, and you have just the area. Remember that sigma 0 is 1, okay? You have just the area of the hypersurface. And this constant is this constant here. All right. And this omega n minus 1 is the area of the round sphere of radius 1. Okay, so here's the question that I wanna answer today. What happens if you change Rn? If Rn is replaced by hyperbolic space? Okay, but so like related question is what is the correct expression for the inequality? We don't even know what expression you have to work with. And what is really interesting is that the answer for the second question comes from general relativity, okay, and especially precisely the Penrose inequality. All right. Okay, so let me talk a little bit now about the Penrose inequality for graphs in Rn. So I'm in the Euclidean case. Okay, this is the work by Lam. There was this paper that showed up on the archive in 2010. He actually didn't publish that. I think he went to finance after grad school. So the paper is there, but I don't think he's going to publish. Okay, so what is asymptotically flat end? Okay, it's just a Riemannian manifold that is diffeomorphic to Rn minus the closed unit ball. Okay, and you put coordinates on this manifold, and you ask that the metric using these coordinates satisfies these decay conditions here. Okay, so this tau is a number greater than or equal to n minus 2 over 2, and you want the metric to be almost Euclidean, okay, Euclidean plus this decay here, and you also want some condition on the derivatives. So in relativity, these models are isolated gravitational system. Okay, so like the mass is concentrated on a compact region. Okay. Okay. So what is the ADM mass? So these conditions here, they guarantee that the ADM mass is going to actually converge. Okay. So what is the ADM mass? Is this limit here. Okay, so you take some derivatives of the metric and you integrate over a large sphere of radius r. And then you take the limit as r goes to infinity. All right. Okay, so at first you are using some coordinates to compute this limit. So it's not clear that this is going to be independent of the coordinates you use. Okay, so this is a result by Bartnik. He actually proved that this is well defined. It doesn't matter what coordinates you use. You just have to satisfy these decay conditions here. Okay. Okay, so this is the ADM mass, and what is the main conjecture regarding the ADM mass? So here's the conjecture: if you have negative scalar curvature, then the mass is greater than or equal to 0. And if you have 0 mass, then it has to be Euclidean space. Okay, this is the famous positive mass conjecture, and it was solved in 1979 by Shane and Yao. And in 81, Witten gave a proof using spinors. Okay, a very elegant proof. So you need some topological condition, okay, that the manifold to be spin. All right, so let me talk about the Schwarzschild manifold, and this is going to give you the equality case in the Penrose inequality. Okay. So the Schwarzschild is this manifold here, which is just Rn minus a ball. Okay. This m, it's a positive parameter. Okay. It's going to be actually the mass of this metric. So with this metric here, okay. Okay, and if you pay attention, the boundary is going to be a minimal hypersurface, and more than this, it's going to be what they call outermost. Okay, there is no other minimal surface containing this one. Okay. Okay, so what is the Riemannian-Penrose conjecture? So if you have a manifold here which is asymptotically flat, okay, you have those decay conditions on the metric, and you have like a boundary which is outermost and minimal, okay, of area A, then the mass has to be greater than or equal to this, okay, this power of the area. All right. Okay, you have to ask non-negative scalar curvature as well. And the equality holds if and only if this manifold is the Riemannian Schwarzschild. Okay, so you actually have a family, a one-parameter family of manifolds now that give you the equality. Okay, so what does the outermost minimal surface means physically? It means like a black hole. Okay. Okay, so this conjecture was confirmed for dimension 3 when the boundary is connected by Huskett and Irmanen. So the proof is using the inverse mean curvature flow, which we're going to see in a minute here. And then Bray gave a proof using a conformal flow. And Bray's proof works for general gamma, general boundary, okay? Doesn't have to be connected. And then, like in 2009, Bray and Daniel Lee, they extended to dimension less than equal to 7, okay? The same proof, okay? And in 2010, that's the paper I was telling you about. This guy, Lam, gave a proof for Euclidean graphs, okay, which was a very elegant and simple proof. Okay, so what is an asymptotically flat function? Okay, it's just a function for Rn minus some bounded open set into R, okay, satisfying these decay conditions here. Okay, so these conditions are such that when you take the intrinsic metric, which is going to be delta ij plus fi fj, so this intrinsic metric is going to be asymptotically flat in the general sense. Okay. So then if you have a graph like this, you can compute the ADM mass, right? So Lam, he proved this formula here that the ADM mass of a graph is the integral of, okay, so let me talk a little bit about the graph. Like the boundary, the components of the boundary are level sets of the function. Okay, so they are parallel to the Rn. Okay. So he proved this formula that it's an integral of something that is non-negative, okay, plus this boundary term here, okay, where h is the beam curvature of the boundary, but inside Rn, okay. So the boundary is on some Rn parallel to the base here, okay? And you're looking to the boundary inside this Rn. And then you have this mean curvature here. All right. Okay, so to get Penrose's inequality, you just need to relate this with the area. Okay. And that's exactly the Alexandrov-Fenchel inequality. Okay, so here's the connection between Penrose inequality and this inequality. So when we saw this, we asked, whoa, there should be a connection between the hyperbolic one and the hyperbolic version of the Penrose inequality. Okay. All right. Okay, so let me skip this actually. So we actually in a previous paper we proved this formula of Lamb. We showed that it doesn't need to be a graph. It has to be a graph outside some compact set. So we proved a similar formula. Okay. So you have this vector field x bar. Okay, and then you have the angle function, which is the angle between x and the normal to the hypersurface. Okay, and P here is some hyperplane. Okay, and we asked that the boundary arrives, like the boundary is orthogonal to the hyperplane. This guarantees that the boundary is a minimal hypersurface of M. Okay. So we actually proved that the formula holds for this situation also. Okay. But you still need to be a graph to get some kind of Penrose inequality because you have this angle here. Okay, this is the angle between the normal to the hypersurface and the vector field En plus 1. Okay, so you need that to be non-negative. So you need to be a graph. All right. So just a few remarks about this. I don't want to spend too much time. That this formula here is based on a flux type formula. Okay. So the first time that it showed up in the literature, I think, is the paper by Alias, Brazil, and Colóquio. Okay, so what is an asymptotically hyperbolic manifold? So what you do is you take this model here for hyperbolic space, okay? So you fix a local orthonormal frame on the sphere, okay? H is the round metric on the sphere. And you consider this frame here is a frame now on the hyperbolic space, okay, FB. All right, so you're gonna have some decay conditions like you had before. Okay, so so the manifold is asymptotically hyperbolic if you can find some diffeomorphism C such that these decay conditions here hold. Okay, and this tau is greater than or equal n over 2. All right. So you, as before, you use this guy here to get coordinates. Okay. Okay, and then our chart that satisfy these conditions, okay, coordinate system that satisfy these conditions, we're going to call it admissible. All right? Okay, and then we have these results by Crucial and Nagy. Okay. Let me skip this. And okay, so what is the mass in this case? All right. So the mass is not going to be a number anymore. It's going to be a vector now. Okay. So you have this vector space here, n. All right. So these are the functions that satisfy this equation here. Okay. And so you're gonna have, so the mass is gonna be a function or a vector, if you will. The mass applied to this function, like, is this expression here. Is a limit like the one we had in the Euclidean setting. Okay. But now you have like a functional, not only like a number. Okay, so what is this epsilon? Is the difference between the metric and the background metric, the hyperbolic metric. Okay. All right. So like the limit exists and it is finite if the coordinate system is admissible and the difference between scalar curvatures is in L1. Okay? And another way you can compute this limit is using this formula here. All right? It's not good, so. Okay, so this is just saying what happens if you change the manifold using an isometry. Okay, so the mass is going to change like that. Okay. This A is an isometry at infinity. Okay. So the space n, if you use this model for hyperbolic space, this space n is going to be this one. So the first function, which we call rho, is hyperbolic cosine of r, and the other ones are hyperbolic sine plus times the standard embedding in Rn. Okay, so on this space n, we put a pseudo-Riemannian metric now. Okay. So the first function here, the inner product with itself is 1, and the other ones, the inner product with itself, it's minus 1. Okay. And we ask that rho be future directed. Okay, so we defined this inner product, this semi-Riemannian inner product on this space. All right. Okay, so if you are on that other model that I introduced before, rho is going to have this expression is going to be given by this expression. Okay. So I mean, you can instead of the functional, you can consider a vector. Okay. You just take pi to be the functional applied to rho I. All right. So we get two information out of this vector that are independent of the charts. One is the causal nature. The other one is this number here. Okay. So the theorem by Khrushchev and Herzlich, actually they proved that this vector is always future directed and time-like. Okay? And it's zero only if you are only if Mg is isometric to hyperbolic space. And if you have a boundary with mean curvature at most n-1, then the vector is time-like. Okay. All right, so we have some other related works here by Wang and Anderson, K. Galloway. Okay. They removed the spin assumption, but like the dimension is less than or equal to 7. Okay. Okay, so you can. So let's look at this the number given by this expression. Okay. So you can change the manifold using an isometry, so that this number is actually the functional applied to this function rho, which is the first function that showed up when we were describing n. Okay. All right. So we call charts that satisfy this, we call balanced. Okay. And so here's the analog of the Schwarzschild manifold when you are in the hyperbolic setting. Okay, so the AdS-Schwarzschild. So, so if you take R equals R0, R0 is the root of this equation here. If you take R equals 0, you get a minimal surface, and if you take R equals this number here, you get a constant mean curvature hypersurface. Okay. So you have actually two formulations of the Penrose inequality in the hyperbolic setting. One is with minimal boundary, which is this one here. So the mass is going to be greater than or equal to this number. Okay, so this thing that showed up before shows up here, but you have this extra term. Okay, and the equality is if and only if the manifold is the AdS-Schwarzschild. And you have a constant mean curvature horizon conjecture. Okay. So only this term shows up. All right. So not many things are known about this. In fact, you only have like one of the only results that there are there. It's a result by Neves, which shows that the approach used by Huisken and Newman doesn't work in this case. Okay. So you can do the same thing that Land did in the Euclidean setting, in the hyperbolic setting. Okay. All right. Okay, so I'm going to consider two boundary conditions. One is the minimal boundary condition. The other one is the constant mean curvature. So in the minimal one, I'm going to ask my boundary to be on. Oh, let me go back a little bit. I'm sorry. Okay. Okay. I'm gonna use this model for R for Hn plus 1. Okay? And I'm going to consider graphs here now. So for each t, I have a hyperbolic space which is totally geodesic. Okay. Okay, so I'm just defining what hyperbolic asymptotic function is in order to like get a asymptotic hyperbolic manifold when I get the intrinsic metric. Okay. So I'm considering these two boundary conditions. The first one is my boundary is going to be on some slice HTN. Okay. And I also assume that the manifold meets this slice orthogonally. So this guarantees that the manifold, the boundary is a minimal hypersurface of M. Okay? The other condition, gamma lies, the boundary gamma lies on a horosphere. Okay? These two horospheres here that we call balanced horospheres. Okay? So, and I assume that M meets the horosphere orthogonally because I want to guarantee that the curvature is constant equals to n minus 1. Okay? So I have a formula like Lenz's formula in this setting also. All right? So this R here is the difference between the scalar curvatures of the manifold and the hyperbolic space, okay? And you have this angle function here that the normal makes with the vertical Killing field, okay? And you have some boundary term. So we have to compute what this boundary term is in both cases. So in the first case, we get something just like we did before. So remember that the horosphere intrinsically is just Euclidean space. So you can do this just like Lamb did, and get a Penrose inequality in this case. Okay. The other case is different. You get this row here. Okay. And then this was obtained by Dog, Guiquot, and Sakovic. Okay, but they couldn't prove the desired inequality. Okay, we need this inequality to finish the Penrose inequality in this context. Okay. Okay. So what we did was we attacked this problem, and we were lucky that there was a work by Gerhardt on the inverse mean curvature flow in hyperbolic space. So we could use that. That hard part was already done. Okay. Let me just mention a similar work by Brendel, Hung, and Wang. Okay. They got a very similar inequality, but in a general, in a family of spaces, okay, not only hyperbolic space, but in hyperbolic space, their inequality is actually a little worse than ours, okay. Okay, so the idea is to use inverse mean curvature flow to prove this inequality. And we actually found two monotone quantities under this flow. Okay, so we used the work by Gerhardt. And another important thing is this inequality here by Brendel. Okay, this P is the is the support function. I didn't put it here. Oh, I'm sorry. Okay, so P is the support function. Okay, so we have these quantities here, and you compute the variation of these things under the flow. Okay, and let me go to the variations. Okay, so you can put the variations here. And this first inequality is just Newton's Maclaurin's inequality. Oh, this is Brendel's inequality, actually. Okay. So with this one, yeah, just a minute. So with this one, you can prove that. So that's the first monotone quantity we found. And then the other one is this one here, this L. Okay? So you have two. We have one that is J minus K over this power of the area, and we have L also. Okay? So, and then, which is not easy, you have to compute what happens at infinity. Okay? This was actually quite hard. Okay, so you flow these quantities, and you know what happens at infinity. And at time 0 is exactly what you want. Okay? And then you get the desired inequality. Okay? So let me go back to the inequality. So you get that. So we were very happy with this. And it's amazing for me that you actually you go to physics to get the expression that you need to prove. Okay, so just a few remarks. The equality case, it follows from the work by Huang and Wu. Okay. Their work is for the Euclidean setting, but it's the same thing goes through. Okay. And I also want to remark that a lot of people, like after we posted on the archive, there were like several papers like doing this kind of thing for higher curvatures. Okay, there is a group in Germany doing that, and we were actually quite happy about this. Okay, that's it.